Hello, my dear viewers. Today we are proceeding with our series of chemical equilibria, and we are going to be delving into the concepts of pH and pOH. Now, in chemical equilibria, the concepts of pH and pOH are very important as they are used to describe the acidity or alkalinity or basicity of a solution, and they are related to the concentrations of hydrogen ions and hydroxide ions respectively in a solution. So this is what we are saying, that pH is directly linked to the concentration of hydrogen ions, or sometimes we use hydronium ions. Then pOH is directly linked to the concentration of hydroxide ions within a solution, and we shall later see that if we have the pOH, we shall be able to tell the pH of that solution. Now, the power of hydrogen that we call pH or potential of hydrogen is the measure of the concentration of hydrogen ions in a solution, and is usually defined by the negative logarithm to base 10 of the concentration of hydrogen ions, or another one can write it as the negative logarithm of concentration of hydronium ions. And then the pH scale ranges from 0 to 14. So when pH is less than 7, we say that the solution is acidic because we have higher concentration of hydrogen ions and low concentration of hydroxide ions. Then when the pH is equal to 7, then the solution is neutral. Here, the concentration of hydrogen ions is equal to the concentration of hydroxide ions. And this is typical of pure water. So pure water has a pH equivalent to 7. That's why we say pure water is neutral, because the hydrogen ions concentration is equal to the hydroxide ions concentration. Then when the pH is greater than 7, the solution is basic. In other words, it's alkaline, in a way that you have more of the concentration of hydroxide ions, and then you have less of the hydrogen ions. And let's look at an example of how we can determine the pH. So if the concentration of hydrogen ions is equal to 1 times 10 to the power negative 3, this is molar, or moles per liter, then the pH, which we said is the negative logarithm to base 10 of the concentration of hydrogen ions, will be negative logarithm of 1 times 10 power negative 3. This is the same as having negative logarithm base 10, logarithm of 1 to base 10, then plus a minus of logarithm 10 to the power negative 3 of base 10. Here we have applied the rules of logarithms, and then this becomes 0, and this 3 comes and multiplies here. So we'll have we'll have 3 times 1, because logarithm of 10 to base 10 is 1. So this becomes 3, and such a solution is acidic, because we can see that the value of pH is less than 7. Let's look at the power of hydroxide ion, and this is the measure of the concentration of hydroxide ions in a given solution. And pOH is equal to negative logarithm of the concentration of hydroxide ion. Now, on the pH scale, the pOH scale also ranges from 0 to 14, is from 0 to 14. So when pOH is less than 7, then this solution is acidic. Now this solution is basic. When pOH is equal to 7, this is neutral, because the concentration of hydroxide ions is equal to the concentration of hydrogen ions. What about when it is greater than 7? Here, it is acidic. We shall learn that pOH plus pH is equal to 14, that is at 25 degrees Celsius. Meaning that if I know that pOH is greater than 7, then I can put a value greater than 7. For example, let me take 10. So I will have 10 plus pH is equal to 14, meaning that pH is going to be 14 minus 10, which gives us 4. This one is acidic. So you must understand the logic between the pH scale and the pH scale. You can use this expression, which gives you the relationship between pH and pH to determine the pH of that solution. And this is valid at at 25 degrees Celsius. So we have just said that, and this comes from the fact that the product of the concentrations of hydroxide and hydrogen ions is equal to a constant, and this is equal to the ion product of water. So if we take the concentration of hydrogen ions, we multiply it by the concentration of hydroxide ions. This should give us Kw, which is the ionic product of water at 25 degrees Celsius. And this is equal to, this Kw is equal to 1 times 10 power negative 14. So it is a constant and is equal to 1 times 10 power negative 14. That is at 25 degrees Celsius. So if I take logarithms, take log to base 10, both sides, meaning I'm going to have logarithm of concentration of hydroxide ions times the concentration of hydrogen ions. This is equal to logarithm of 1 times 10 power negative 14 base 10. Using the rules of indices and logarithms, I'll find that this is logarithm of concentration of hydrogen ions plus logarithm of concentration of hydroxide ions, because I'm multiplying here, meaning if I'm to separate this, I will introduce an addition here. So this is equal to logarithm of 1 plus logarithm of 10 power negative 14. A further simplification will show that this is logarithm to base 10 of the concentration of hydrogen ions plus logarithm to base 10 of the concentration of hydroxide ions. This becomes 0. Logarithm of 1 to base 10 is equal to 0. So I will have negative 14 logarithm of 10 to base 10. Yes, the rules of logarithms tell me that I can have this 14 go the other side. That is a rule everyone has to understand in mathematics. So now I'll come and say this is equal to 1. I'm having logarithm to base 10 and I'm saying it is logarithm of 10. Logarithm of 10 to base 10 is equal to 1. So I multiply it by 14 negative. I'll have negative 14. So what I'm going to do, let me divide by negative 1 throughout. So this becomes negative log of the concentration of hydrogen ions plus minus negative log of the concentration of hydroxide ions. And this is giving me 14 because this and that is going. But we said this itself is the pH and this represents pOH. Therefore, pH plus pOH is equal to 14. That is true at 25 degrees Celsius. So we are going to be looking at dissociation of acids and bases. Now for a strong acid and base, these dissociate completely in water. These dissociate in water completely. So what does that mean? I can represent them with an equation that is unidirectional. In other words, I'm having an example of hydrochloric acid, which is a strong acid. It dissociates in aqueous form to form hydrogen ions and chloride ions. This is a strong acid. Then a strong base, like potassium hydroxide, will completely dissociate in water to form potassium ions and hydroxide ions. Now, this tells you that If, for example, you had a concentration of potassium hydroxide of 0.05 molar, it would give you the same concentration of hydroxide ions of 0.05 molar. The same thing with the acid. If I had 0. For example, 1 molar, it would give me a concentration of hydrogen ions of 0.1 molar, because all the hydrogen ions are going to be alone. I mean, this hydrochloric acid or this strong acid completely dissociates to release all of its hydrogen ions. Now let's look at the case of weak acids and weak bases that are represented by reversible reactions. So the weak acid and weak base, these dissociate in aqueous form or in water to partially produce the ion. In other words, they do partial dissociation. So for partial dissociation, we are going to represent an example of ethanoic acid. Ethanoic acid is a weak acid, and therefore it slightly dissociates or partially dissociates to produce ethanoate ions or acetate ions and a small amount of hydroxide ions. So take an example of acetate acid, which is a weak acid. It partially dissociates in water to form ethanoate ions and some hydrogen ions. Likewise, if we talk about a weak base, such as ammonium hydroxide, so in aqueous form, it also partially dissociates, produce ammonium ions and a few hydroxide ions. Now, with the weak acid and weak base, we shall be required to determine what we call the dissociation constants. So for an acid, we have Ka, and for a base, we have Kb. Take an example of hydrofluoric acid that is slightly dissociating in the water. It produces hydrogen ions and fluoride ions. Or another one would write it like this. I add water there, and this dissociates to form hydronium ions and the fluoride ions. So the hydronium ions is now a component that has the hydrogen ions, and it is what is going to determine whether this solution is acidic. So to get the acid dissociation constant, Ka, this is going to be the concentration of the product, that is the hydronium ion, times the concentration of fluoride ions divided by the concentrations of the reactants. And here the only reactant that we have is HF in aqueous form. So the concentration of hydrofluoric acid is what is going to be at the denominator. So in these reactions where we have equilibrium, we find that liquids and solids do not take part. So for that matter, whenever you write the formula for Ka, never put anything that appeared to be a solid or that appeared to be a liquid in your equation. Now for a base, that is a weak base that we are talking about, Kb shall be also the concentration of now hydroxide ions and the other ion divided by the reactant. So if we take an example of ammonium hydroxide dissociating, it will slightly dissociate to form ammonium ions and hydroxide ions. The Kb for this reaction, or the base dissociation constant, is going to be the concentration of ammonium ions times the concentration of the hydroxide ions divided by the concentration of ammonium hydroxide. So here you can now calculate the concentration of hydroxide ions and then be in a position to find the pH of the solution. because you already know that pH will be 14 minus pOH, that is at 25 degrees Celsius. 25 degrees Celsius is desired because that is the most common room temperature that we might have, and that's the normal room temperature. So all the factors that we refer to, our measurements are taken at that particular point. So in the next lecture, we are going to be looking at the examples and calculations on how we can be able to determine the pH of the solution given the concentration of either a base or an acid. Let's talk about pKa and pKb values. So sometimes you might meet things like pKa and pKb values. What does pKa mean? This is the same as negative logarithm Ka value, and then pKb is equal to negative logarithm of Kb value. So therefore, I can have pKa plus pKb equivalent to 14, that is at 25 degrees Celsius. Because we said that Kb times Ka is equal to Kw, which we called the ionic product constant, or what we called the autoionization constant for water. Therefore, if I take logarithm to base 10, both sides here, I'll have log of Kb times Ka equivalent to log of Kw. But remember, at 25 degrees Celsius, Kw is equal to 1 times 10 power negative 14. Therefore, I'll have logarithm of Kb plus logarithm of Ka, which is equivalent to logarithm of 1 times 10 power negative 14 of base. And this also becomes what? This is equal to logarithm of 1 plus logarithm of 10 power negative 14. And this is equal to, remember this is 0, and this becomes negative 14 logarithm of 10 to base 10. So therefore, K log of Kb plus log of Ka will equal to negative 14 times 1, because this is log 10 of base 10, which gives you 1. So you multiply by negative 14, you'll have negative 14. So I'm going to divide both sides by negative 1. So I'll have negative log of Kb plus negative log of Ka, and this gives us 14. So if I refer this as Pkb and I refer this as Pka, then I'll have to finally say that Pka plus Pkb will equal to 14. And this is true at 25 degrees Celsius.